We are already live.
Okay. Oh. Yeah.
Hi. But that's fine.
Hi, everybody. Yeah. So I think we just start, right?
Yeah, we started. People coming in.
Okay. Yeah. So, yeah. Hi, everybody. Thank you very much to come to this second fireside chat about the Majorana research. So my name is Shidai from Hong Kong University of Science and Technology. So I'm currently on the moving process to UC Santa Barbara. So, but for the visa problem, I still stuck in mainland China. I have to wait for my visa and yeah, doing everything remote at my home. So. So during this last year, during this big pandemic, I was trapped in half-time in Hong Kong and half-time in mainland China. So during this year, I've talked to many colleagues in Hong Kong and mainland China about this Majorana research. So recently, this retraction from the Nature magazine actually attracts a lot of attention in Hong Kong and the mainland, and many colleagues actually expressed their concerns to me about basically these concerns. We can divide them into two types. So the first is about the science itself. So it's obviously that the retraction of this paper is moving back of the Majorana research a little. So many people are concerned about the future of the Majorana research. Is the topological quantum computing is this field still worth doing, or from the founding manager, is this field still worth investing, right? So there are those questions, and also there are questions about the data treatment. So because we never publish all our data, all the raw data, so we only publish some of them, and we need to like rearrange those data in such a way that it can make the data actually much easier, much understandable to general audience. So for that purpose, we always need to treat our data in some way, but what kind of treatment is allowed and what kind of treatment is probably on the boundary, and what kind of treatment is definitely cross the line. So we have such kind of discussion in private in Hong Kong and mainland China for many times. And my feeling is that there is, of course, there is a line, but this line is so far not very clear. It's a vaguer line there. So yeah, I think this retraction will remind us that we should probably have more discussion on those issues also openly. So that will actually help us to make our data more like transparent. So to help people to have the more easier access to those data and review those underlying physics much easily. So I think I just pass the stage to Susan. So Susan, please.
Yeah. Hi, I'm Sue Coppersmith, and I'm at the University of New South Wales. And I just want to say, I'm going to put a thing in the chat that the way we're going to do so Xi and I are the moderators, and we're just basically going to be organizing the questions. So feel free to put questions in the Q&A. So there's a Q&A tab, just put them in there, and we'll do a certain amount of amalgamating, and we'll be asking the questions of the speakers. We'll read them out at the end of the talk. And want to thank you for participating, and feel free to and just type in the questions when you think of them, because again, then we have a record of them and we'll put them in. So I'd say I'm going to hand it over to Vincent and to Sergey right now. Thank you.
Thank you, Xi and Sue. Oops, I just need to get the presentation going. All right, so Sergey and I have prepared about 20 minutes introduction where we will take turns, cover a broad variety of topics. So first about ourselves. My name is Vincent Mourik and Sergey Frolov is the other participant. I know Sergey from my PhD days back in Delft in 2010, 2012. Well, Sergey was a postdoc in Delft. And we got to know each other through collaborating on the Majorana research back in Delft. We have since moved on. I'm now doing a postdoc at UNSW in Spinker with research, and Sergey continued to being active as an experimental researcher in Majorana research at the University of Pittsburgh. So a very broad and brief introduction to Majorana fermions. What are they? So they were proposed in the 1930s by the man Ettore Majorana, and they are a very paradoxical particle in elementary physics. You look at the equations and at the prediction, and it is a particle that is equal to its own antiparticle. And this is very strange. So usually there's a mirror symmetry between particle and antiparticle, but now it is as if you're in front of the mirror and there is no mirror image. It is identical to yourself, like as in the painting by the painter Magritte. Now, mathematically, we express that with that equation that is on the screen. And what this tells you from a physics perspective is that the creation of a Majorana particle is the same as the annihilation of such a particle. And this is just, yeah, it's a strange, quirky particle in elementary particle physics. For 60, 70 years, this research belonged in the realm of particle physics. And it wasn't until the late 90s that theoreticians realized that these particles also have a relevance to condensed matter physics. The theoreticians started to come up with increasingly more concrete ideas how to engineer and realize these particles in a condensed matter system. And what is crucial to realize here is that those are called quasi-particles. They are a collective behavior of all the constituents of your piece of material. And the best analogy I can think of, or an easiest analogy I can think of, is think of a pond of water, throw a stone in it, see the propagating waves. Such a wave you can describe by a wave equation. It's a single phenomenon, but it's built from billions and billions of individual water molecules. This is exactly what we're trying to achieve here in the solid state. Build these particles as an, these Majorana particles as an effective description of the collective behavior of the system. So in the early, so in 2010, there was this proposal to do this in a nanowire that came out from 2 theory groups. And that was a very concrete, at the time, realistic proposal that we were in Delft really, suited to attack that problem. That was the start of my PhD, and Sergey was in the middle of his postdoc then. We set out, and after about 1.5 years or so of hard work, we had a really exciting period where we managed to make a first generation of these devices to work. So you can see one on the screen. It has superconducting material contacted to this nanowire in the center. And these devices are operated very much like a transistor. So there is an electric voltage that you apply to control the current. And by measuring the amount of current flowing through these devices, you learn something about the electronic states in these devices. It was a very exciting period. We saw the first, what we thought back then, glimpses of the presence of Majorana fermions in these devices. And we got that published in Science. We made it onto the cover, and it was all a very exciting period, and we are proud of that work. I want to emphasize that this was a real concentrated team effort. So I was one of the PhD students. Kun Zhou was the other PhD student. We were shared first authors on that paper. Sergey was the daily supervisor in the lab, like really helping us carrying out these experiments. And then there's the 2 nanowire growers, Sebastien Plissard and Erik Bakkers. So they provided us with the nanowires, and Leo Kaunhoff, of course, was the chief investigator, supervising the whole team and facilitating all these complicated experiments. Now, ever since we have been wondering ourselves, the community, like, did we really measure Majorana fermions? What we saw back then. Well, we don't know the answer to that with certainty. Perhaps we didn't even measure them back then, but we made sure that there is at least one Majorana in this experiment. And it is here on the cover of the Science magazine. You can see the face of Majorana hidden in the tip of the nanowire. All right. Why do we care so much about these particular particles? And this is a fundamental difference between elementary particle physics realizations of Majorana fermions and solid state condensed matter realizations. These quasi-particles in condensed matter systems, they have a very peculiar property that the geometrical arrangement where they are in space, that encodes information. And changing that arrangement by moving them around actually changes that information. And this is a way to perform actually a quantum computation. This is quantum information that is hidden in these particles. So if you would attach world lines to these particles, like in particle physics, and those are the red strands on the screen, you get, and you move these particles around and you trace the world lines, you get these very complicated, intricate braiding patterns. And that is the computation you are performing. And if at the end you do a measurement to figure out the final arrangement of your particles, that is the answer of your computation. And what is so interesting about this is that this is a robust process, theoretically. If you shake one of the individual strands around a little bit, the pattern stays the same. So you have a way here to perform a quantum computation in a robust fashion. On this slide, time runs different. It runs from right to left. We start in 1997, and this is the amount of papers in the field of Majorana. So this is Web of Science keyword Majorana. And you see that up until the late 2000s, there is this steady output of about 100 papers a year across all disciplines. So this includes particle physics, with the keyword Majorana. And then with the appearance of the Fu and Kane proposal, roughly, there is this steady increase in the amount of papers in this field. And that is when the theory and experimental community really started to focus on realizing these particles. And I think there's a key message in this slide. This whole research field, it's not about a single paper, nor about a single group. This is about a whole community that is very, very focused and excited about realizing this physics in condensed matter systems. We should not forget that this is, it's much bigger than one person or one article, one group. Now, this extensive focus, it goes much beyond just the scientific community. This also covers the popular press. So all the popular scientific outlets have paid lots of attention to this research field throughout the years, but also all the major news platforms. And there is a very clear reason for that, I think, and that is the distinct and early interest that Microsoft as a commercial partner took in this specific research. And the reason for that is that Microsoft is pursuing this research to establish this as a novel quantum computing technique, as an alternative to the existing platforms.
Okay, I take over from here, and we fast forward to 2019 and the events surrounding this Nature paper, Quantized Majorana Conductance, which is now retracted, which is frankly a relief for us, because as you can see from the timeline, it has been a monumental project for us to be involved in this situation. So it started even before October 2019, maybe in the summer, when in my group in Pittsburgh, we were doing experiments on these kind of nanowire devices, and we were getting similar data to what is in this paper, but we could not verify the conclusion that this is Majorana. And that eventually, I just approached the authors of this paper and asked for some additional data. And they kindly provided us with a PDF file, which was kind of a notebook style presentation with pictures of data, which were sufficiently clear for us coming from the same group in the past to understand those data. And we analyzed it for a while, and we found some errors, which I will present to you a couple of these errors in the subsequent slides. And for the full errors, you can look on Zenodo at our extensive slides. Now we had a discussion with the authors. We were not satisfied with their explanations, and we approached Nature. At some point, the authors agreed that the paper needs to be retracted, and then there was a long wait of almost a year before this retraction became official. So these kind of retractions are very, very long affairs. Now, let me show you some of the things that we found. And like I said, it's not everything, but these are some of the easiest to explain in the slides, in simple slides, issues that we found. So one thing we noticed is that on the bottom here, you have a figure 2, a key figure from the paper with red dark stripe in the middle is this evidence of Majorana. And in the data that they shared with us in those notebooks, there was this piece in between the pink lines, and it was cut out, and the two parts of the plot were then glued together, and this was not disclosed in the paper, which is a problem. And this is, but this is not the main problem of the paper. The main problem is that it biases your view of this result towards thinking that this is a continuous and smooth and long feature. Here's another one that's very easy to understand. Now, what they show in the paper, this is now figure 3, is these orange data points on the right. But the phrase that they use is notably the ZBP height comes back up to the quantized value and does not cross through it. What this means is this trace plots the ZBP, the zero bias peak, and quantized value is 1 on the vertical axis. So 1 is right here. And indeed, the orange points do not cross 1, okay? But in the full data, what they shared, you see that immediately at the edge of figure 3, this trace goes above 1 and goes pretty far high above 1 to 1.5. And these data were just simply hidden. Now, ZBP that goes above 1 is a problem for explaining this as Majorana. It's a major problem. Here's another thing we found. This now relates to figure 1. So I showed you 2, 3, and 1. These are the key figures. And figure 1 shows magnetic field dependence of inductance. And now here again, we have these color maps. All of them look similar. Here, starting from the bottom of each plot, we see 2 of these bright lines evolving and merging in the middle. Okay, and this is again a zero bias peak formed at finite magnetic field. So this feature is again investigated as Majorana, and it's important for the paper that this value reaches exactly 1. And this is the only plot shown in the paper. However, in the larger data set, we found about 20 other sets, and we found values all over the place, 0.6, 1.3, and everything in between. There is nothing special in the full data set about the value 1. This is what we found. Now, what does this mean for this paper? First of all, I want to say that by no means it means that data were fabricated or falsified. So data were not made up. It's all real data. The data were manipulated and data were omitted. And together, these two factors amounted to claims of the paper, this quantized Majorana conductance. It is unsupported by the full data. Interestingly, from the notebooks, which were just pictures of data, we could not pick up this other issues, though we suspected it. But there was also signal miscalibration that the authors themselves found, and they pointed out in their retraction note. Now, in order to see that, you need to see the original source data files, which we were not given. So we had no chance to discover this issue by ourselves. But we think the key issues are data manipulation and data omission.
All right. I want to talk a bit more about biases when you conduct research. So in this context, we consider two types of bias. The first one is on the left. That is what we call biased post-selection of data. So you gather during your experiment this large data set, and then you zoom in on a single feature that you particularly want or like, or that fits your narrative, and you ignore everything around it. And in this case, that is that beautiful nanowire in the center, and you ignore all the messy ones around. There is a solution for that. It's a simple solution, so that others can check and verify what you did, namely share your full data. If you share the full data of your publication, external people can verify how you selected your particular data for the figure in the paper. Then there is a second type of bias, which is when you are conducting your experiment and you're really focused on proving a certain hypothesis or finding a certain feature, and you ignore everything else that doesn't fit your narrative so well, or so you really single-mindedly focus on that thing. I think that always happens a little bit in experiment. It's inevitable. And then the question is, did it lead to a bias that is unacceptable? And that's very much like the old-fashioned radio, where you tune through all the stations and you stop at the news station that tells the news that you like to hear. Now, the solution for that is to give insight in your experimental procedures. If people have questions about it, share your lab journals. Show them how this happened, how you came to your conclusions during the experiment. So for the Delft, for the Delft experiments, we have asked for the full raw data and insight into the lab journals, which we haven't gotten yet. And one thing I want to point out here, that is in most countries, in many countries and jurisdictions, actually as a researcher, this is something you are obliged to do. For example, in the Netherlands, there is a code of conduct, and it's a very nice, clear document that really states explicitly that if a peer asks these type of questions, and they are legitimate questions, then yeah, you need to share these as a researcher. However, we want to propose and stimulate you all, especially the scientists in our audience today, to go a step beyond that. And this fits in a recent phenomenon in the past decade or 15 years or so that's called open science. And this is the trend that we are witnessing throughout the sciences to make science more accountable, more verifiable, and open to the broader public, in principle even to the general public. And you, as a fellow scientist, you can actually really boost that movement and help this on the left side in this infogram by sharing your data and sharing your lab journals. And really, we would like you to actually forget these words that we see so often in in Nature papers, etc., like additional data available upon request. Why do we need to request this? You could stay on top of this and take initiative and share your full data just up front. And this is not something that is particularly difficult. In most cases, nowadays, all data is taken electronically. In many cases, our lab books have a digital character. They are Python notebooks or so, Jupyter notebooks or PowerPoints or whatever. So you convert these to a PDF format or so, and you put it all in a folder with some level of organization in there and maybe a README file in that, but that's about it. You zip it up and you can upload it. And there's a fantastic platform for that. It's called Zenodo. It's managed by CERN. And it's instant publication when you hit the publish button, and you get a nice proper DOI that allows you to include it in your reference list and everybody can reference it.
And so I will talk about Majorana research as an important topic also. What of it? Well, there is a kind of bad news and good news situation. We do not currently believe that this phenomenon has been established, has been discovered, because there is an alternative explanation, which I will briefly present to you. But the good news is that we have perfected our measurement technique since 2012. We now can tell Majorana from not Majorana from our measurements. And so now what we need to do is improve our nanowire materials, at least that's the hope, to fine-tune it and tailor it into the Majorana regime so the future is bright. Okay, so what is this alternative explanation? The top picture you see here is what Majorana look like in a nanowire. The blue box is a nanowire, And Majorana is an electron split in two parts. It's one electron split in two parts, and the green part and the red part are wave functions. So they're kind of blobs, you know, in quantum mechanics, particles are waves. Now, this is what we want for quantum computing, etc. But we may have a non-ideal situation where the two Majoranas are not split too much. They're just split a little bit. That's the middle picture. And finally, we can also be in a situation where the green and the red parts are really on top of each other on one end, and that is just a normal electron, completely unsplit. And this is still interesting physics, but it's nothing to do with Majorana. However, all three of these can give similar experimental signatures. So here's an example, for instance. On the left, you have a data set in red, white, and blue. So the blue is like water, and in the middle, this white peak is an iceberg sticking out. That's the Majorana signature zero bias peak, was considered as Majorana in this paper, was discussed as Majorana. And now on the right, it's a different color scheme. It's a volcano surrounded by black. This orange feature in the middle is a very similar looking feature, but it is definitely absolutely not Majorana. It is Andreev bound state. So when I say we perfected our method, well, this is my platform. I believe that if we demonstrate these 5 signatures using the same nanowire, we have, with high degree confidence, have established Majorana zero modes. So in the interest of time, I will not go through them right now, but we can come back to them if you like. And so what's been happening is there's 5 signatures, and I've plotted all the papers that came out since 2012 by how many signatures they have shown. And you can see that some of them go up to 2 or 3, but none of them have demonstrated all 5. So this is what we need to do: show all 5 signatures, and that will be Majorana. Now, what we want to, what the path is to demonstrating these 5 signatures is materials engineering. I have become a materials engineer in the last several years. I've explored all kinds of nanowire materials, their shells, the preparation of their interfaces, TEM, and other characterization with electron microscopy, and growth of superconductors on them. We're making some progress. We're maybe not quite there yet, but this is absolutely necessary to take us to the right Majorana regime. And these are some of the considerations on the screen, what we need to meet. Now, I have to also mention that we're talking about nanowires here because this is our expertise. There is a wonderful variety of Majorana platforms that people are thinking about. Maybe some of the people in this audience working on different realizations of Majorana. And my way of thinking about any new platform is through these 4 questions on the right. Is it reasonable, right? Is it described by a theory that is not predicting Majorana as a distant possibility, but is it something that can actually be realized? Is it verifiable? Is there an experimental tool like a zero bias peak that you can study to verify that it's Majorana or not? And for quantum computing aficionados, is it braidable, right? Can you develop apparatus to grab them and move them around each other to perform this quantum computation? And then finally, if you want to commercialize it, it has to also be scalable. So you could deploy something like an Intel factory and crank out Majorana chips. So what is my thought about the braiding experiment? I think it's a wonderful physics experiment. It's a holy grail, like gravitational waves or Higgs bosons. The reason I think that is because it would demonstrate a new class of particles in addition to boson and fermion, non-abelian anyons. So it's more similar to those big physics experiments in my mind. Now, it may also bring some advantages for quantum computation But I say we have to see. We have to first try to make it and then see how good it's going to be. What drives me is a fundamental physics interest. I think that's the end of the presentation, right? Yeah. So we stop here and we can take your questions.
Let's see. So do you want to go first, or do you want?
Yes, I can go first.
Okay.
I see there's a question in the Q&A. His question is, actually, there's two questions. So the first question is about should nature have strict controls, or the nature should ask the authors to upload their full database, the full data set before the publication? I think this is the question. That means just give all the data set to the reviewers during the paper review process.
Yeah, this is a very good question, very good suggestion, I should say. I think we need to establish all sorts of incentives to make people more aware and more willing to share their full data. And this could be one of them. But perhaps one of the most powerful ones would actually be to do it at the level of the funding agency. Because the journals are still, you want to get your papers into the high impact journals. So that is very important if they would make a statement like that. But think about it, if the money stops coming in from the funding agency because you don't publish your raw data, we will all instantly share all the data we have.
Okay. Let's see. This is a question from Tim Duty. Hi, Tim. Sergey, could you show the summary of the signatures again and give a bit of description of each and like what's hard? And now I'm adding to Tim's question of like, what are the hard things, and what do you think in terms of like what's missing and that next step required?
Yeah, happy to do it. Should be on the screen now, right? Okay. So it's 5 signatures. I picked these signatures because they are relatively easy to demonstrate. All of them are based on zero bias peaks and whether they come or go. So one wonderful thing about these nanowires is that we can kill Majorana in many different ways. We have a lot of control knobs. So the first signature is just a zero bias peak that's somehow extended. So this eliminates the possibility that this is an intermittent crossing of 2 states and they by accident meet at 0 in the middle. That would be an accident. And now if they stick to 0, that gives you some indication that it might be something interesting. Does not prove Majorana by any means. I don't have a slide here, but on my Twitter I showed 4 different scenarios how you can get a sticky zero bias peak. Okay, so you still have a lot to distinguish at that point. Okay, the second one is spin orbit anisotropy. Doesn't matter what it is, but it is one of the ingredients to have Majorana. So if this is demonstrated, then you can believe that this has something to do with Majorana. Phase diagram in electric and magnetic field. This is just comparing to the basic theory predictions from 2010. That Majorana has to live in a finite phase space. So not for every possible electric and magnetic field, but in a confined region predicted by theory. Peak oscillations is because you have 2 Majoranas on the 2 ends of the wire. If they're very far apart, you have a zero bias peak. If they're a little bit close together, they overlap and the peak splits in 2. Think of it as the 2 particles begin to annihilate. When the 2 particles annihilate in particle physics, then there is a gap opening when they're allowed to interact. And the 5th one is really common sense. Majoranas have to come in pairs. They originate from electrons, and electron has 2 parts. Majorana electron is split in 2 parts. and you have to demonstrate both of them. If you just look at one and you don't have the other one, then it could be something else.
It's okay. I'll there's one. Oh, okay. Yeah. So the next one, which is another slightly farther afield, not far afield, but slightly different scientific question, is from Samanti Bhattacharya. And she asks about the interface. That so far they've been done using deposition of the superconductor on the nanowires. And do you think that there are promising prospects for creating the clean enough interfaces using other techniques?
I will take this one. So this applies to nanowires, but also to two-dimensional electron gases, two-dimensional type systems and three-dimensional systems, I would think. There has been a fantastic development over the past 8 or 10 years, basically the period that I was active in this field. There's been a fantastic development in interface improvement. When I started, we were really taking only the baby steps. We were doing the crudest, thing in hindsight that we could have been doing, and we got consequently rather dirty devices. And then the materials community really jumped on this, and they have done a fantastic job here in improving these interfaces. And to be honest, I think this is a success story. It's like fantastic what we are learning and what we have achieved. We have much cleaner systems now, better quality interfaces. And there's also clear indications that there's still a lot of room there to keep going. So we should keep pushing this. For example, the idea to put a tiny shell in between the superconductor and the semiconductor to control the tunnel coupling between the two materials. That's an idea that has been around for a while, but it's only quite recently that people start to experiment with it at the materials engineering level, because it is just very hard. And that's a whole new toolkit that we can start to exploit also as device physicists. So this applies, I think, broadly to all the materials that interface a superconductor, a bulk superconductor to a bulk semiconductor, be it two-dimensional, one-dimensional, three-dimensional. Keep improving as material scientists, keep improving these interfaces. It's absolutely crucial. There's fantastic progress, and we need to keep going. And it is our job, like people like Sergey and me, to then verify this in electronic transport devices, that we indeed get better quality devices.
Yeah, that's another question from Jacinta May. So he or she asked, does the QMC paper, I think the QMC paper probably is the retracted paper, invalidate all other publications in the field of Majorana research? So, and the second one is, did the QMC paper have any evidence for Majorana in the full data set, or did it simply demonstrate ABS? ABS probably is the Andreev refraction, the Andreev bound state. Yeah, please.
You want to go? Go ahead.
I think it's a very short answer, twice no. To be honest, this is a single paper where there's problems, and that is gone now from the record, but it doesn't mean that. Like, that is the point I wanted to make in the beginning with that slide with all the citations. There's a whole community there. There's a vast body now of theoretical work and also a substantial body of experimental work. And of course, that is not invalidated because one paper is invalidated. That work still stands, and we should all critically scrutinize it, go in and be critical towards it. And if it's here and there too positively interpreted, we should point that out, sure. But of course, those experiments stand in themselves, by themselves. With regard to that particular paper, we are convinced that everything in that paper can be explained by trivial mechanisms, so trivial Andreev bound states.
Yeah, I can also add, retraction is a very procedural thing, right? So, it's pretty tedious and careful to prove or convince that the paper is invalid enough that it needs to be retracted. You convince the authors or the editors. There is a process involved. So unless this process is performed for some other paper, there is no direct validation or invalidation. Now, if there were papers based on the retracted paper, somebody said, oh, I also have quantized plateaus, just like they published. Now, this could be a problem, right? If you base your work on the invalid work. Now, certainly all the previous work, you need to look at it separately. That's what I wanted to add.
I was going to ask a question from Wyatt Fine. Sergey, you highlighted at the end of the talk all the different platforms people are exploring for development of Majoranas. Aside from nanowires, are there any that satisfy the criteria you set out on the slide? And I guess I was going to add that there was a paper in Nature Physics by Manfra, which is more a braiding type thing. And so do you have comments on that?
So this is a question for me, I guess. Okay.
Sorry for you, but feel free.
Yeah, so I don't know which one is, Nature Physics Manfra with fractional quantum Hall effect.
Yeah, so I sort of wanted to get your comment on the quantum Hall and then also on the nanowire thing.
Right. So, I mean, the easiest for me to answer is, what are they asking? Criteria, right. So, quantum Hall is, feasible, testable, verifiable, and braidable by interferometry. So it satisfies the criteria and can be pursued just fine. Topological insulators with superconductors, feasible, verifiable, these kind of things. Planar junctions, semiconductor Josephson junction, feasible, verifiable, braidable, probably even scalable. Then there is a class where anything that involves STM, vortices or atoms on the surface, is feasible, verifiable, probably not braidable. There were some proposals, but pretty tricky. So that's because your tool for access to these states is very slow, scanning tunneling microscope. So that's difficult to imagine how you're going to braid them, but it's interesting physics. I mean, there's a lot of systems, so I'm not going to go for all of
them. Yes, I think there's a very good question from the students. So it's from L. Sheen. Dear Sergey, how can you comment for the young researchers, such as students, identify possible mistakes during their research? Because many students may not be able to distinguish between variable data information and it jumped a little bit. May not be able to distinguish variable data information and data that can be proceeded. Furthermore, could you comment on our slide B, or could you comment on slide B shared by WeChat platform? Thank you. Yeah.
Well, for sharing, we will discuss what to do this weekend, I guess, Vincent, right?
Yeah.
We will keep in mind the WeChat.
Yeah.
Maybe you can help us with that, Shi.
Yeah, no problem. Yeah.
Okay, so the question is, I think there are two ways to interpret this question. One is when students read papers, should they believe the papers? And the other one is when students do experiments, how should they handle data and do analysis, right? So it's going to sound a little bit silly, and Vincent, I hope you also pitch in on this answer. At one level, follow your gut. Gut as in, the feeling inside you. If you feel like it doesn't make sense, then, try to scrutinize it. You can ask for data from the authors of the paper, and they're in many cases supposed to share it with you. my principle is respect everyone, trust no one. Okay, I can explain. I mean, it sounds arrogant and mean, but as a physicist, you don't have to trust anyone. You can verify everything. You have the training, or if you don't have the training, you can acquire the training. But there is nothing wrong with asking questions. You can ask questions until you're satisfied, okay? And many, even big professors, much bigger than me and Vincent, are happy to answer the questions. Now, when you do your own research, again, the same principle, follow your gut. If you absolutely can stand by your claim, great. And then you also have no problem sharing all the data and analysis, right? If you have any doubts, double check, triple check, redo your analysis, talk to somebody, okay?
So perhaps what I would like to add to this, I want to focus in on the research side of things. When you are a master's student or a young PhD student or so, like I went through this myself, right? I was doing this Majorana research. We were all very optimistic and enthusiastic. And for a while, I was really convinced that I was measuring it because it looked so promising. And then slowly in the years after, I discovered, like, you know, this is too hard. It's too difficult to find further evidence, and you start to put question marks to your own beliefs. But the point is that having a certain belief, which in hindsight turned out to be not the right belief, I think it is fine, because that is how science works. You should stick to the basic research principles. Do justice to the data that you measured. Like if you have 10 data sets and one of them shows the desired behavior, you cannot ignore the other 9. And that is very basic principles that I think from early on, that's a task for supervisors, I think, to hammer that down. And we as young people, when you are just starting, try and be beware of that. Things should be internally consistent. You cannot have one data set saying one thing and another thing. Like when you're conducting your research, that should raise questions in your own mind. How can I reconcile these? And if you can't, then that should perhaps not be the basis for a grant claim, such a data set.
Yeah, and we will try to do some writing on this topic in the coming months. But it takes a lot of effort, but we will. Actually, I want to say that the reason we're doing this chat and actually doing all of this is for the students, right? We cannot, you know, just let it go. We have to, you know, make it right for the next generation. So this is the main reason why we're doing this.
Yeah, fully agree.
Okay. I'm going to ask a somewhat more technical question, which came in actually before the chat, which is when in these experiments, quite typically, when you look far from the ends of the nanowire, you see a superconducting gap, which is a soft gap, and there are states in there. And how serious of a problem is it in terms of can you ever get a really clean experiment whenever you have a soft gap like that? And what do you think are the criteria for moving forward and really feeling confident about what you're seeing?
The soft gap issue, so that you know that you don't have a perfectly BCS type density of states, but there's all sorts of background in there. I think at a detection level, it is not the end of the world. We can think of many ways why this could be the case. It could be involved, you know, could not even have to do with the section of the nanowire that you are interested in where the Majoranas live. Having said that, it is likely a strong indication that for the long term, the system is not good enough yet to go into the time domain, try and do braiding type of experiments, move in that direction. So I think when you are at in the phase of the experiment where you are trying to establish, do we have this highly interesting zero bias peak? Are we going to try and measure something like the 5 criteria that Sergey mentioned? A soft gap is not the end of the world. You can live with it as long as you can clearly distinguish the zero bias peak from the background. As long as it's a well-defined experimental feature, that's good enough in my opinion. Once you want to move beyond that, it is a serious problem, and it asks for serious material engineering.
Yeah, that's another question from Team Duty. Another physics question for Sergey. You didn't mention the 4-pi Josephson effect. Will this be a unique signature of Majorana, or can you also get this from the ABS?
Right. So yes, indeed, I focused on this zero bias peak that I showed you folks on the screen. And there have also been other proposed ways to detect Majorana. And so Tim here mentioning this so-called 4-pi Josephson effect. It is not unique to Majorana, but I'm sure in a device with enough control knobs, you can identify it as coming from Majorana when you see it. But my problem, the reason I did not put it on the list is because this effect requires 4 Majoranas. It requires 2 segments of the wire connected together. So you can imagine we are now having difficulties with 1 segment with 2 Majoranas. Now, this effect requires 2 segments with 4 Majoranas. So I think even in 1 segment with 2 Majoranas, we can establish them pretty definitively from zero bias peaks.
Okay, I'm gonna ask another question that came in prior to the chat, but so there were, obviously one of the things that was a question in the Nature paper that was retracted was the cutting of the data and not showing all the data. But should it never be, should there never be this thing, or are there criteria, or is this something, I mean, there's, I know it when I see it, but again, the question of data selection and what's the transition between showing representative data, which just happens to look nice, versus misleading, really coming to misleading conclusions. So do you have any comments on that?
Let's first talk about, specific processing steps like cutting or cropping a data set. I think if this fits your narrative and your analysis, this can in principle be fine, but you need to fully disclose it. So it needs to be probably written already in the figure caption in the main text, and then in the supplementary, I think you should simply share the full data set as you took it, and there should somewhere be a justification why you did that specific analysis. And there are many legitimate scenarios I can think of where you want to do that, just to make the point, and it is scientifically fine. And as long as you disclose it, there's no issue. Really, the same, in my opinion, applies to the overall data selection. How do you go from 1,000 data sets to the 10 that you stick in the article and in the supplementary? Ultimately, you should disclose the full data again then. I think that's really important. And there should be some justification in your supplementary or in your method section or so. There should be a justification that you did the right thing, in the sense you selected a representative data set, and that should be verifiable when people look at the full data set. So selecting data is, we all do it. It has to happen, because you cannot, in a short document with a concise story and a concise point, you cannot put all the data in. That doesn't make sense.
Right,
but you should be able to defend
it. Just pick 4 graphs that, if you don't see any others, can pass as Majorana, where you know that you have 100 others that don't fit Majorana.
Yeah, that's another technical question from Hongqi Xu. Sergey, braiding is a crucial issue beyond your 5 criteria. Do you have any suggestions for doing this in nanowire system? Hi,
Hongqi. Thanks for joining. Yeah, so indeed, you're right. So you also, it writes that the keyboard scheme may not work. So the keyboard is creating lots of electrodes and really tuning the Majorana along like a keyboard, like playing the keyboard, moving particles along the wire. Wouldn't it be spectacular, though, to realize that? I think that would be amazing. Certainly, I think that braiding should be done by moving Majoranas in space, or at least coupling, decoupling them to each other so that there is a space aspect to it. There is a scheme also, an interesting scheme for projective measurements. So you kind of do a lot of measurements. Qubit people will understand. You basically project, do charge measurements, and nothing is moving. So that can work for a qubit, but it's from a physics point of view sort of not satisfying. I think they should be moving. Now, how can they be moving? Well, if you don't like gate moving, you can move them with magnetic flux. We have a proposal in PRB how you can do it with 4-pi Josephson effect with flux. You can, rather than moving them with a keyboard, you can just use one gate like a transistor and couple and decouple 2 Majoranas across the wire. That can also correspond to braiding. So there is some, at least, pathway to braiding. There is a lot of apparatus that needs to be developed, but there is a pathway.
Oh, there's a question that's coming twice, so I'll ask it, which is how to incentivize the checking, because if you say, oh look, I checked it and it didn't check out, that's sort of not highly incentivized in current organization. And again, it's tricky, but I sort of, there's quite a bit of interest in your thoughts on that question.
I'm of the opinion that it asks for an overhaul of the peer review system, honestly. That is where this should happen. This belongs in the realm of peer review, but the way it is happening now is that, especially with high impact papers that go to prestigious journals, they are sent typically to prestigious eminent scientists in the field, because they have a long history on the topic and they are true specialists, but they're also the most busy people in the community. So sometimes these people, delegate it and they do it within their team, or sometimes they do it themselves. But it's not realistic always to have these people spend weeks on verifying all the details of the data. Like, these people don't have the time to ask for full data and then dig through it, for example. That's not going to happen. It's not realistic. And I think this is a big flaw and weakness in our peer review system as we have it. So I don't have, the best possible solution for that either. But I think we live in an era where, through online means and social media type platforms, definitely we can come up with something better. Like, why don't we have an active discussion somewhere online that is moderated, for example, based on an archive paper, and then you give the authors the chance to respond to that and improve on the paper.
There is PubPeer, which is you can even allows for post-publication reviews. So
yeah.
Even if paper is published, you can post your comments on any paper on the internet on PubPeer.
Yeah, I'm thinking that something like that is what we need, and we need to formalize it perhaps a little bit. Like, it needs to be more accepted throughout all layers, by the young people, by the old people, the experienced and the inexperienced, and embraced. But I feel that if we really want to tackle these issues, that is the sort of solution we need. This is just the peer review system is a little bit broken in this respect.
So I agree with Vincent. I think I can rephrase it by, we should normalize this process. We should normalize checking, discussing, research, making it more open. I mean, my vision is when I take data, I just post it on the internet and we discuss it in real time with colleagues. We don't even, we write the paper at some point later when we all agree. We all work together, the whole community, but that is some distance away for sure. Where we are now is a pretty bad situation. We should stop at least impeding efforts to check, right? So now it is painfully hard to get access to data, convince people that there is something wrong. This last year was very hard for us, just emotionally and just amount of time it takes. And we went through this exercise, and now we know all the pitfalls and problems in the system where the process simply stalls. And institutions, governments, they can do a lot about fixing that. Journals. If you read my Nature opinion, it offers some of the ideas for what we can do.
For example, something I can think of immediately, like if we all find it, normalize and accept to share data, wouldn't it be a nice few weeks project for a PhD student to once throughout the PhD or twice scrutinize a certain experimental paper? That would be a perfect thing to do. And the student would learn a lot, and hopefully in 9 out of 10 cases there's no issue whatsoever, and maybe once in a while you intercept something. But even that is impossible because it's so hard to get access to the raw data or to the methodology.
I was going to do one more question. It's one, but I'm going to do one more question that just came in the chat about Sergey's recent Nature physics paper. The barrier at the right end, is it possible that the barrier at the right end is too thick or not optimized? And that's the reason why there was only a peak at one side. So again, a technical point, but.
It's possible.
All right.
We swept the barrier and we swept the gate outside the barrier and inside the barrier, and all that data is on Zenodo. In that case, we shared so much data, we're writing another paper based on the already available data. So that I just have to finish it, and there will be one more paper. So, but yes, it is a possibility. But this question is from the category, well, how do you know it's not Majorana?
Yes.
Extraordinary claims require rigorous proof, right? So we demonstrate that it's most likely not Majorana, but there is always a possibility.
The burden of proof lies with the exciting, with the high impact hypothesis. We know of trivial mundane mechanisms. Okay.
Yeah, I mean, initially in the optimistic era, right, there was a question about that also.
Yeah,
Optimistic era, when you show the first signatures, I mean, even at that point, we checked so many things, and in the supplementary of the 2012 paper, there is 3 other zero bias peaks that contradict the Majorana. If you look there, right? But at least you don't know about another explanation. So you also have this, well, what can it be else, right? And now in 2018, you don't have that luxury. There is something else, Andreev hypothesis, and there is a Majorana hypothesis. And now you have to prove one against the other, and that's a high burden of proof.
And yes, so now in the Q&A, there are a couple of questions regarding the peer review process. So I just combine them. So people are asking in the current peer review system, the review process are all based on the data they show on the paper, not the full set of the data. So do you have some more suggestions to improve that? Do you have more suggestions to the editors of the journals to make it better?
So whenever I review a paper, the first thing I do, I ask for more data. I just do it automatically, and I do it right away so that people don't wait, right, for my review. I don't begin to review until they send me more data. And most journals go along with it. They pass on the request to the authors, and most authors comply with it right away. They provide data very quickly. Like, with Delft, we, after 1 year, still don't have the data. When it's in peer review, you get the data in like a week. Okay, so that's very effective, but it's a little bit tiring because every time you have to ask. Now there's one journal, Nanoletters, which this thing didn't work. I said, I want to see more data. They told me, well, if there isn't sufficient data, you just have to reject the paper. Now, I think that's counterproductive. I wanted to give the authors the benefit, to share more data with me so I can fully assess the paper. And I think the journals should do that. So next time you get a paper for review, ask for more data, because once it's published, it's harder.
Okay, so it's a little past 1 o'clock my time, so we've been going for an hour. I guess I don't know whether we want to stop, or there was one more question which I was going to put in the queue, which is my understanding of the review was that it was not that the paper, it was felt that the data for the paper did not support the conclusions, but there was not academic misconduct. So there was a question about academic misconduct and consequences, but my understanding is that that there was a investigation and it was found that there was data, you know, that there was, what was it? Wasn't called rampant optimism, but anyway. And whether you have any thoughts about just in general the consequences for misconduct and penalties for not following through sufficiently carefully in these kinds of situations. So anyway, and that's going to be my last question, just because everyone has a life.
About this specific paper, I think we have had a role here of exposing the scientific problems. And it wouldn't be correct if I then also do the investigation into the possibility of misconduct and have an opinion on that. That is not my role. That is nor Sergey's. Like, that's, we don't have the powers and the means, and we are biased because we have already done the scientific part of the exercise. But it's up to TU Delft, and TU Delft, I don't think they have finalized that process yet. So there's nothing I can nor want to say about that. That's not up to me. More generally, I don't know, what do you think, Sergey? Like, if in case there is misconduct, what should happen? It's a very difficult question.
I mean, again, there is a procedural aspect to it. If you're found to have committed misconduct, there could be consequences for you. You can be fired, you can be expelled from professional societies, stripped of honors, degrees, even sometimes. So this can have very severe consequences. And I think that also, of course, motivates the discussion of when should this be applied, and by whom, and so on. Who decides? Who's the judge? So there are some processes, they're underdeveloped and they don't often find people guilty. So that's the status. But I can offer a different angle on this. What do we as a community believe is a no-no? Let's not use the M word, misconduct. Let's not use this word. What's a no-no? What is not allowed to do? Okay. And everyone, I think, would agree that making up data is a no-no. Like, you draw the data in PowerPoint or make up a table of numbers or copy paste in Photoshop, or that's a no-no, right? Everyone agrees, but many people think that that's it. That's the crime and everything else is not a crime. So what we are trying to show here is that biased data selection, you pick data that is not representative of your set, leads to a false claim, and your paper becomes invalid, and it's a no-no. You did not make up any data. You're not like Jan-Hendrik Schoen, but you wrote a paper that has nothing to stand on. And this is achieved through biased data selection. And then, of course, this is a sliding scale, right? How much bias is in your data selection? A little bit or a lot, right? So, try to make it zero. And if you can't, try to make it as small as possible.
Yeah, so maybe I can add one more point to Sergey's suggestion. As Actually, I read the investigation report from the 4 experts. They are really well written on the scientific part. I really enjoy reading them, and they explain everything to me as a theoretician at the beginning. It's always a headache for me to understand all those details, but their report was written in such a clear way that even a theoretician like me can understand it quickly. So I really appreciate it. But then I think for those 4 experts, they behave on this, they were like 4 judges to make a final conclusion if this misconduct or not. But I think it's put just too much pressure on them, because there are, as Sergey just said, there are like very severe consequence and this can lead to. So it probably just put too much pressure on them, on the 4 experts. So my suggestion is probably we can release this kind of pressure in if we just form 2 type of committees. So first is the scientific committee, which is formed by the real experts working in this particular field. So their task is not to make a conclusion. Their task is to write a scientific report, just like this one, make every point clear, but without any conclusion. But then we form another committee, just behave like a jury. The jury will will read the scientific report written by the real experts very carefully. And then after that, the jury will vote. So then it's just like a trial. So just try to remove the burden a little bit from the real experts to.
Well, you know, it was interesting in the case of Delft. It was supposed to be already like this, by my understanding, because there is a research integrity committee at Delft University, which is internal, and it just takes the report and makes their own report.
I see.
Okay.
So that's
actually, I don't understand why they made the external experts also comment on this aspect.
Right.
In the Q&A box. I think we can sort of group these into ones that are more physics related and ones that are more culture of science publishing and open data related. I'll start with the one that's gotten the most upvotes, even though I think I know the answer to this. So, the question is there really a mechanism to make sure that the raw data is really the original raw data without some sort of curation happening behind the scenes? I will take the liberty of answering that as an experimentalist and saying, well, probably not, unless one wants to really get into digital signatures and all kinds of fancy bookkeeping. But I'd be curious to hear what the speakers have to say.
Should I take it, or Vincent, you want to take it?
Well, one comment I can make is that we're talking about deep level of frauding here then, I think. And I think when you're an expert in a specific field, you might not see that for a few individual data sets, sure. But if you have a data set in its totality, I would be highly surprised if you're a real specialist on that topic looking into it, if you don't see inconsistencies. Like sometimes things go wrong in an experiment, or things go exceptionally well. Faking all that, not just faking an individual data set, I would think would be really hard. So I agree with your initial answer. At the same time, I hope that, I just hope that it doesn't happen often. And I also hope that a keen observer is still able to pick it up.
Yeah, I can add to that when we take data and when we took data in Delft, all kinds of parameters of the system were recorded, timestamps, even as you take data, the data point timestamps were recorded. So it's quite an effort to completely fabricate data sets.
Just to be clear, I think the issue is less about fabrication and more about whether there was some curation done before and said, you know,
Yeah.
here it is. But
Yeah, here the question
without
is
any
more,
processing. Yes, I mean, the raw
after
files
the-
are very clear, and we know how they should look, and we would recognize them. Of course, for experiments from another lab, we might not be able to tell, but they have a lot of technical details, and they're kind of ugly. You want to look for ugly files.
Yeah. I would say there is no general mechanism. You have to be an expert and knowledgeable of the field in order to recognize this. So it's not super easy for the people that are not, you know, doing the same kind of measurement to recognize it. So I think this is the problem in spotting.
Also, as long as your purpose is not to seek out fraud of any kind, but just to understand the measurements, curated data is perfectly fine. Right, and there are multiple benefits to just sharing it, not just to make sure you are not lying, but just to enable all kinds of open discussions, reinterpretation, and so on.
I will say disconnect to the next question that I see in line here. Like, are there any ways you can think of other than complete data sharing to better the peer review process so that these types of errors are can be detected more often?
Yeah, so of course, there's all kinds of things that can be improved in the peer review process. I think that the way we do it now, anonymously with journals, has many problems. For instance, if a paper is rejected, it can just be sent to another journal without any changes and be accepted there. And all the input that the referees gave is lost. Right. So more opening up that system one way or the other has to happen. We need to see the reviews, what was commented, and I can be a bit revolutionary here, but eliminate rejections. Right. So just attach reviews to each archive, whoever did it. You got your paper reviewed in Nature, those reviews get attached to your archive identifier, something like that. And then you can also discuss with reviewers.
okay, let me see here. Let's shift a little bit to the physics because there's some questions that have cropped up both in the Q&A, and a couple of people emailed very similar things beforehand. So the first one I would say is, can you comment on the relevant, paraphrasing, but the other platforms people have seen evidence related to Majorana's, the chains of atoms on surfaces, for example, in the STM experiments. What do you given that some fraction of your 5 criteria involve things like gate voltage dependencies and stuff, I mean, are there, what do you think about tests one could apply to the STM data? And do you think the STM data is prone to some of the same challenges, even though it's a very different physical system in terms of identifying topologically trivial versus topologically non-trivial bound states?
So here I'm going. So my main expertise is of course with nanoice. That's what I'm familiar with. Definitely the physics are more generic than just that system. So I would basically recommend. So my upfront answer is, for every individual material platform, I don't know which set of criteria to give for that specific platform. Okay, I can think of that for the one I'm familiar with. I can make it very specific, but I can comment on the strategy to follow there. So the physics of the Majoranas is very particular. It is always it has a space element in there. They have a specific location where they are in the system. It is a phase transition, so there needs to be a range in parameters where it creates. And these are the type of signatures that you want to look for. So whatever your, in STM, it is also tunneling measurement. So that is what you want to find. You want an extensiveness in phase space. You want it to be a localized state.
Well, so basically what Vincent is trying to say, I think, is that for each system, you can define its own 5 criteria. So Doug brought up a different platform from the cloud that I had on my slide, and this is these atoms on a surface. Started beautiful work from Princeton, and for that there'll be 5 criteria that are different, but you know, some of them will have overlaps, right? There always has to be 2 Majoranas, because if you break an electron, there has to be 2 halves. You know, they cannot just perish 1 half. So there has to be some consistency there. Maybe length of the chain is another parameter. Obviously, you don't have a gate voltage, but you can come up with a different set of tests for each platform. The beautiful thing about nanowires is that Majoranas can be destroyed in so many ways in this platform. And so we can test the hypothesis to death. We can cross-check and check all kinds of electric and magnetic fields and field orientation and so on. So we can make sure that we are really looking at Majorana.
Somehow related to this, I see in the question some question about other platforms. So for instance, chains of magnetic atoms on superconductors. So there are a couple of questions about this. Do you think it is possible to see the Majorana there? Are these reliable? Are there advantages, disadvantages?
Yeah, so that's the one we just talked about, and it's definitely possible to see Majorana there. There is some papers that say that it has not been seen out there, and there are some papers that say that it has. So in that sense, it is at a similar stage as nanowires. One difference is that they're not braidable. So you cannot demonstrate this non-abelian property, at least not very easily with that system. So you can study Majorana physics, but not the braiding physics.
Okay.
Doing one more physicsy thing that, again, before returning to other questions of culture, I think. So again, trying to capture the flavor of some of the questions here, as well as a couple of the ones that were emailed. A couple of people have asked, is it possible that there are real difficulties? Well, I guess you've sort of addressed this. Are there real difficulties with really doing this nanowire approach? Meaning, is it possible that Andreev bound states and disorder at the surfaces and stuff are just unavoidable? Related questions were things like, you know, how can you really always tell the difference between these Andreev bound states and the Majoranas? And a more technical question is, you know, there are other pieces, there are other measurements that were done, for example, by the Marcus group, looking at things like little Parkes effect, parity effects. And I guess this may be too technical for a broad audience, but you know, how does that figure into your 5 criteria? And you know, can those also show up from Andreev bound states, or are they really Majorana specific?
So I think you started with inherent difficulties basically in the nanowire research, and so I view them. I think here we need to appreciate the beauty of the theory. The theory is very robust. It's a rather simple theory that results into the prediction of these Majoranas. And it's rather generic. That is why it can be applied to so many different material systems. There is no a priori reason to think that it cannot happen. That means that the difficulties in the nanowire system, but in any material system, they are an engineering problem, I would argue. One of, can you beat The odds of, for example, disorder was mentioned. Disorder, yes, is not good. If you have too much disorder, it breaks up your nice homogeneous properties in your system. You don't want that. Can you control that through clever materials engineering and hard work, dedication? Can you bring that down? I don't have the answer to that. I think at this point in time, nobody really has, because it's ongoing research. What I can say is that I have, this started about 10 years ago or so, the research field, specifically for nanowires. We are not there yet. At the same time, I've seen an amazing progress, and especially at the level of materials engineering. We have now a toolkit that we as device physicists can utilize, that it's so much more versatile and complex and sophisticated than we had a decade ago. So if I look at that and I think positively, I see absolutely no reason why it wouldn't happen one day. There's no fundamental showstopper there. And this is a broad comment, I think, that applies probably to most of the systems, but for sure to nanowires.
Yeah, I can add also that Doug mentioned, there's 5 criteria that I stand by, but people have tried to find Majorana in other ways. And yes, they are all fully consistent with Andreev states. So if you cannot see the 5, no point looking at others. 5 are the simplest, the most basic.
Thanks. Another question is really a bit more fundamental. It reads, its Majorana are so fragile, then is this really a good approach to combat the coherence issue with quantum computers? I have to say I had the same question. Can you comment on that?
Yeah, so of course, like I said, we know so many ways to kill it and destroy it, and we can't even find it so far. So how can it be good for quantum computers? Well, I don't know if it's good for quantum computers. Like I said, my framework, I'm in the physics department. I think of it as CERN or LIGO, looking at the black hole. That's how I think about it. It may become useful for quantum computing. I can tell you about quantum computing that, like Vincent said, there's been amazing progress also in quantum computing. We even have quantum computers. I even used a quantum computer, and it's awesome. It's amazing. I love it. But this quantum computer is a toy. It's like a Lego toy of my son. I enjoy playing with it. I enjoy learning physics of a few qubits with it. It is not the useful one that will crack the internet and so on. And to get there, we may need to reimagine completely how qubits look from the atomic level all the way up. Qubits that make it practical may look completely different. And so all ideas are on the table, and Majorana is one of the wackiest ones, but hey, why not? As a physicist, I'm perfectly fine with that.
Okay, I was attempting to answer a question by typing something. I will get back to it. So it's not so much a question as it's become a discussion. The top ranked thing on the Q&A is about whether people have to be careful about papers that have been in the literature now for 7, 8, 9 years that in their original wording make strong claims. Do people need to go back and now that everyone's understanding of how challenging it is to do this distinction, do people need to go back and modify those or put disclaimers on those? And I think it's being discussed actively on here. I don't know if you have anything you want to say about that.
Now, it's something I think about a lot, of course. Sergey and I and the whole team, we were part of the very first papers, and Sergey calls that in the slide he discussed, he calls that the optimist era. I take comfort in the fact that back then, when we did that experiment and we wrote that paper, we tried to do a thorough job, and I stood behind what I wrote back then, and I still stand behind that, in the sense that with the knowledge I had back then, that was perfectly suitable to write. we also need to acknowledge that there is progress in science, right? Sergey also said now, like, yeah, I don't think Majoranas have been measured. A statement I agree with, which also means that in our paper back in 2012, most likely we didn't measure it. So I think the distinguishing, which is of course subtle and not always so black and white, how to answer that is it in this ballpark? Can you legitimately claim that progress of science has changed your understanding of your work in the past? Or was your work in the past, whenever it was, if it was recent past, distant past, was it not solid? Was it not rigorous also back then? I think it matters really what happened at the time you published. Did you do a rigorous job back then or not?
Well, I can also comment that the title of the 2012 paper is Signatures of Majorana Fermions. And according to my list of 5, it identifies 2 signatures out of 5. Okay. And this list of 5 is something I wrote down, not for this chat. I didn't whip it out. I wrote it back in 2012. I wrote down this list. Now, the optimist part is that, of course, in 2012, I was very sure and hopeful that in the coming few years, like 2013, 2014, we will uncover additional signatures, like signature 3, signature 4, and of course, signature 5, which will seal the deal, finding 2 Majoranas in the same nanowire. Now this has not happened. And we learned in 2014 that another effect can produce a similar signals. Okay. Now, 2014 is after 2012, but 2014 is before 2018. Okay, so that's how you can tell which people knew and which people didn't about Andreev bound states. And then the question here by Damon asks whether the paper should be retracted. No, there is no data omission, data manipulation. The paper is written in a very careful way, and we plan to share full data from that paper online. We have received permission from all the co-authors. So it will be on Zenodo. And we will work from 2012 forward, sharing all the data, certainly from my lab, but hopefully we will also convince Delft folks to share all of their data. So it will be all out in the open. Retraction is a very special thing. There has to be a particular reason for it, like an error or, a lie, something like that.
Okay, I've noted a couple of questions that I can merge. And it reads like, if you can comment on the role of the external pressure, like corporate partnership that might play, well, I would also say funding agency, or the pressure of to be, I don't know if you have a non-permanent job and so on. All this kind of pressure that might play a role in facilitate this kind of misreport. And the other half from someone else, it seems like the author did do the manipulation intentionally, but did share the actual data. Could there be an external factors forcing data manipulation? So this is more on the reason for this kind of problems. Can you comment on that?
I'll take that second question. I basically categorically refuse to comment on why people do things. It's not my task nor my position to comment on that. I'm a scientist, like most of the people in the audience, I presume. I had this specific expertise to look in this specific paper, which is what we did. We found problems and we raised them. I find it, I just find it pointless to try and understand why things happened a certain way or who did what or etc. I don't want to comment on that, honestly. But
more generally, of course, we are all under pressure, even with permanent positions. I mean, even in academia rather than in a company, there is a lot of pressures for funding, for promotions, and so on, and for getting your students the jobs that they need and deserve. So at a general level, this is a factor in why people want to have their papers in Nature. Why can't they just have them on archive? We refuse to comment on what are the factors in any given situation, but system-wide, it is absolutely a factor.
Yeah. So, I mean, system-wide, perhaps we could take this as an opportunity to reflect also on the system that we built ourselves. I mean, academia is such, and because it has been built by the people working in academia. So perhaps we could take the opportunity to go, beyond the current incident and think, as a perspective, we can still change the system and, I don't know, find different ways to evaluate like the excellence of people and not by like the number of papers or the brand of the papers. So this somehow is changing already in some funding agency in Europe, I must say. So I think it's we can make, take this as a positive opportunity to do better our job. So
yeah, I think Zeila,
for the future,
mentioned funding agencies. I think that's the type of entity that can really change it the fastest. To have calls for a change of culture or is effective, but it's slow. And as soon as money changes course, we will all, we can just stop ignoring nature and science in all our decisions, like for funding or promotion or hiring, in 1 minute, as soon as they tell us to do so. So the government has the biggest power here.
Yeah.
Just to segue from there, so two things. First of all, it's 11 o'clock. It's the top of the hour. Trying to be mindful of different time zones. So we should probably think about wrapping this up soon, I guess, but we're going to keep going at least for a little while, continuing to answer questions. One related thing about what you were just saying, Sergey, about the culture and what drives these decisions. Certainly, as you're alluding to, the funding agencies, hiring decisions, a lot of these things these days hinge on this idea of high impact publications in high impact journals. What do you think about non-publication of negative results? And that, this is asked by Steve Simon, but I think it touches on a couple of questions that were also emailed. How should we think about, journals historically are rather reluctant to publish negative results or refutations or even reproductions of things. Because there are claims that it's not original or it's not exciting or it's not as groundbreaking or more appropriate for a specialized journal. What do you think about all these issues?
Vincent, you want to say?
I don't have a solution, but I think it's a real problem. It's actually a very real problem, and I can relate to it. For example, in the second half of my PhD, I measured many more zero bias peaks, and there was not really an avenue to publish these. They ended up in the thesis. Still, I think it was very valuable research that would have contributed and added to the field somehow. But because the pressure is so high to, especially when you have made a first big claim, right? The pressure is really high to make the next big claim, make the next big move, and so what I'm trying to say is this is a very real issue, and finding a way to disseminate work that is not brandable or hypeable to the extent that it makes the cover of a Nature or Science paper, it's probably one of the most important pressing issues that we should try and deal with, because there's a lot of new information in there and valuable insights often. They get lost.
Yeah, I can add to that in fact, there are some promising signs, and the journals, even the high impact journals, deserve credit. in the last year or so, literally a plethora or a small plethora, a plethora, I don't know how to say. A bunch of papers came out with negative results on Majorana in science, in nature physics, in nature communications, and I was very pleased to see that. I think that really is going to help us move the discussion forward. You know, there's been a kind of a change, and sometimes the journals are, as I learned, are actually happy to publish negative results, but the researchers are afraid or don't think it's worth their time or presume that the journals will not be interested. So from my personal experience, having published a negative result in Nature Physics, incidentally on this quantized Majorana business, I encourage all of you folks to reach out to your editors, and they might actually be open to considering your results.
Yeah, no, I mean, I will comment even a negative result is very important because it saves a lot of time to all the other people and it's really valuable. It's part of an encyclopedia and it has a value by itself. So it's really worth sharing publicly and publishing it.
Yeah.
See. I don't know, we can swing back a little bit towards some physics, because there's still a lot of questions. A couple of questions are about, you know, material improvements, and I'm trying to synthesize them together here. Material improvements, what is really the criteria for disorder? How do you quantify disorder? You know, is there some well-defined target for materials quality?
Yeah, I should probably take that. Yeah, so it's a little bit tricky. In semiconductor industry, we have a parameter called mobility, right? Like a HEMT is a high electron mobility transistor, suggesting that it is, you know, electrons move through the transistor without bouncing and scattering. And this is really what we want, except nanowire is very small and narrow. And so it is difficult to define a parameter as straightforward as mobility in this case. So what we've been using is, on the one hand, very advanced materials characterization tools, like we go to synchrotrons or transmission electron microscopes, which cost millions of dollars and are state of the art, to see the atoms in the structure and see if they are all in the right places in the nanowire. But on the other hand, we just do our experiments, and man, we can see stuff. This is such a powerful technique, these zero bias peaks. So if you see a forest of resonances of these peaks going through, that's a dirty device. Okay, and if you don't, that's a clean device. Now, it's a little bit slow to improve based on that, because you need to make this advanced device, cool it down and measure. It's a lot of work, but it's very direct, you know.
So
I just tried to put the in the chat for everyone, the 5 criteria, and I summarized them very, very briefly in text.
So there are more questions about the science part. So I'm reading one. Does the quantized level along the transfer direction of the nanowire can influence the formation of Majoranas in a semiconducting nanowire? So you can have low electron density by tuning the back gate and use a single channel, but does the presence of the other channel empty can contribute somehow? It's a bit technical, but I don't know if you want to take it. So it's a comment on the transfer direction of the nanowire and its influence on the formation of the Majoranas.
Yeah, I'm not sure I fully understand the question. I think I'll have to think about it.
Yeah. then
I think, well, I think the discussion is about, yeah, okay, thank you for posting.
yeah, I wrote it. It's a bit complex and
Yeah,
a bit
so
technical.
I think the discussion here is about, you know, are we in the right parameter space to even see Majoranas in these nanowires? That's how I can generally reformulate it. And the answer is we may not be. We may have too many electrons in the wire, and that's what the person who asked the question means by these quantized along the transverse direction. There may be too many electrons in the wire, and when there's too many electrons in the wire, theory says that eventually you won't be able to see Majorana. So then we need to understand how many electrons we have, which is a little bit tricky, and try to lower the number of electrons. But okay, that's a clear thing to do, and it's something we have already been trying and will continue trying.
And it's not a showstopper, so it's not black or white. You don't need to have a single channel per se. You can work with basically a number of channels, but not hundreds. Yeah.
There have been some questions about about essentially I'm trying to merge some of these things since time is going onward, about, you know, the what you need to do to get sort of a lab culture in place of really having everything in a format where it's shareable in a nice way. You know, getting people to actually have lab notebooks and things like that annotated and properly organized. I don't know if you have any thoughts on beyond, you know, ruling with an iron fist over your group and telling them, listen, you have to document things exactly the following way. If you've got some general ideas on how you get that culture in place.
This is a very relevant and interesting question to me, because I'm hopefully, if all goes well, going to start my own small team in a couple of months' time. So I'm starting to think about this actively. I don't have perfect answers yet. I think from a management perspective, I think you need to accept as a supervisor that overhead is involved. If you want, you cannot accept, you know, a perfectly systematic way of data taking and analyzing if you don't accept a level of overhead in terms of time that people need to spend on that. So I would argue that an important aspect of it is that resources need to be allocated to it. It can be at the individual person's level, but it can also be, for example, to try and attract an external programmer that helps you clean up your measurement code or your analysis code, or etc. Resources at that level. I think there's lots of modern tools, though, that are very helpful. Nowadays, there's lots of notebook style programming happening, Jupyter notebooks, etc. in Python, that are really quite easy to naturally facilitate data logging and systematic data taking and logging on the fly. It's inevitable still that the individual researcher, I think, needs to spend a lot of time as well on curating this, or you know, bringing this to the next level then.
Yeah, the way I see it is, first of all, well, the way, Doug, you asked the question, I mean, properly documenting your research is not optional. It's not a matter of iron fist or being a dictator in your lab. This just has to be done by everyone, and PI, professor, research leader is responsible for making this happen. And so explaining it to all the team members how to do it. Now, I guess the practical dimension is incompatibility, you know, using different formats and so on. And this is a problem that needs to be addressed. And I hope that something convenient and universal kind of takes over virally. But at the very least, we have spreadsheets, right? The most basic thing, a table of numbers, like in the ASCII format, that can be read by a script of any kind. right? That can be shared. And the other thing I want to add, don't sweat curation, pretty presentation of your data. Just share it. Just share it how you took it. Now, if somebody is interested and can't plot it, they will ask you for help, but at least they will see that it's out there. And this is already amazing. Let's worry about, making it all compatible later. If we worry about it before, we will never start. We will never go to the next level. Just share how you took it. If it was in a proprietary software, whatever, just share it.
I would say it's more a cultural habit that we have to build. It's not really the tool. The tool is just a tool. I mean, then we can use whatever technique it looks good. But the important bit is really to have the culture and to be transparent with the work, and to document what we do. And this, I think, is useful for the researcher himself or herself at first, because then you know what you are doing, you know where to find your data, you know how to reconstruct the physics or the chemistry that you were studying. So also you might come back in a second time if you have a new idea, and you might reuse that set of data if you back it up properly and you know how to retrieve it. So I think it's good. It's a little cultural shift that we should also take into account. No, that should help. So I have a question from the mails. It's about the editorial process. So do you think the editorial process of high-profile journal will change with more high-profile retraction? What direction should it take? This comes from a student in Slovenia.
Vincent, or?
Good question. Sergey, what are your thoughts?
Okay.
You take off.
Yes, absolutely. I think the editors are actually all good people, and but they sit in their own bunker, and they need guidance. They need discussions, open, discussions about what we, what would be good, what are the good ideas, right? And they're trying. If you pay attention to, what they do, how they change their policies, they're trying. Nature now requires some kind of data sharing, not full data sharing, but some kind of data sharing. All those little disclaimers that you may be annoyed with, author contributions, and those are all in response to either scandals or, push to be more open, more explicit about certain things. And I think this will continue. Some journals now share peer reviews, anonymized peer reviews, and so it's just they're trying different ideas, and they should be praised for this, because they have the resources and they are full of clever people that can actually force others to do things differently. If nature tells you share your data, you will. If I tell you share your data, you won't. Simple as that.
I think also funding agency, at least in Europe, they asked to share the data in open format as much as possible. So this is one, we commit to that when we get money from this kind of funding agencies, then we have to, there is no choice. So it has to be open. So that's also, I mean, I think the funding agencies can also enforce this.
Yep.
Okay. Someone asks about whether it's possible to do unblinding, whether you can do everything blind and then unblind at the end. I'd be curious for your thoughts on that. I mean, in principle, one could do that, though in practice in condensed matter, the one reason why this works in enormous high energy collaborations is that you have big teams and people are all responsible for little pieces. Whereas often in condensed matter, the total number of people working on an experiment might be 3. So it's pretty challenging to do things in a way where people don't know what the settings on the lock-in amplifier are and things like that. I don't know. What do you think, folks?
Yeah, I think it can be formalized like this. There is a very clear study design for high energy physics, which can be followed and can include as a step blinding of the data, right? You set up your machine, the collider or whatever, you press a button and then the thing goes through all the steps, including data analysis, without human intervention. In condensed matter, we have a multi-dimensional parameter space. Nanowire devices have up to 10 control knobs. So it's a 10-dimensional parameter space, and each data point is, let's say, 100 milliseconds to acquire, right? So you cannot explore the full 10-dimensional parameter space where each data point takes 100 nanoseconds. So you can take 10 data points per second, and you have 10 control knobs, right? So if you could do that, you acquire the 10-dimensional cube of data and then run it through the script that then tells me whether Majorana is there or not, then it could be blind. But otherwise, it relies on my personal intuition and my skill of navigating in a 10-dimensional space to the interesting regime, right? But I have to disclose how I did it. But it is a pretty personal. It's more of an art form than a science in this aspect. I guess high energy physics is more science, and this is more towards art. You still have to share what you did.
Okay.
Yeah. There are many more questions, but somehow some are related. I would say for the deep physical origin of the Majorana, I don't think it's the place because we will need a lecture, perhaps.
Yeah. I'm actually pasting a link to something in there, but like, yeah, if someone wants to write the great popularly accessible article about Majorana, the realization of Majoranas in condensed matter systems, that would be great.
There were, last year, 2-3 couple of reviews, which were quite nice. I happened to read that. So perhaps this could be useful. At least it was good to have an idea of to approach the field because it's very complex, and you have topological physics, you have superconductivity, you have nanowires technology. So it takes a while to digest all this information, I think. But there were very nice 2 or 3 pieces around last year.
Yeah, so one of the pieces is written by me with 2 friends, Jay Sao and Mike Manfra, and it's in Nature Physics. I don't know if it answers all the questions, but it talks about the state of the field, but along the lines that obviously I shared today.
So, yeah, that will also answer the question in braiding in nanowires, at least to give an idea.
Yeah, I mean, braiding is easy. You make a network of wires, you make a T-junction, and then you can braid.
People are asking if you're going to share the slides or the references from this, and also if you're going to share the recording of this.
Probably.
Yeah.
Okay. I guess the challenge is in what format can one share a large-scale recording? I guess you could put it on YouTube if you really wanted.
We are having another discussion with for people who live in an opposite time zone in a week. So probably we'll share after that.
Okay. someone's asking, can you share the links to the review papers in the chat?
Yeah, there was Elsa Prada has put, I guess it's a reference. I confess I've read both Elsa Prada review and your review, Sergey. They're both very nice.
Thank you.
And also I had a look at the Physics Today, and that I think is for people that are not in the fields. That was also that was very nice. I would say people really starting that don't know anything about, that is very accessible.
Well, I can also tell you that there will be more on the subject, but as one of the questions is about embargo, I cannot tell you what and when, but soon.
Yeah. So
I'm assuming that from your talk about how you think that this can be achieved, the question about, do you think it's possible, that it's impossible, that it might be impossible to achieve this, your answer to that question would be no, you don't think it's impossible to achieve this.
yeah, I think that's the question everybody, let's say, wants to have answered.
Well, okay, since it's already like past the time, and well, I don't have a drink in my hand, but in that spirit, you know, what better ideas we have to be busy with. This is such an amazing undertaking to try to find Majoranas, try to braid them. I just love it. You know, it's feasible enough to keep working on it. You know, there aren't really many more things that I can point to that would be equally exciting. You know, this is a provocative thought, of course. You can bombard me with your counter examples of here's 10 more exciting things. I dare you, I challenge you to do that.
And the other thing that I said it earlier, but let me repeat it once more. We have come a long way. It's just we are no way there yet. There's still a long way to go, but it's not as if we are not moving. I don't think we are stuck or so. This I fully disagree with. There's been amazing progress in the past 8 or 10 years or so that this field has been really active. And yeah, take maybe a little bit of expertise to see that progress, but not even all that much. There's just so much cool new materials now that are also amazing, not only for Majorana physics, but also for other quirky physics experiments in quantum transport, but also in more quantum, you know, quantum computing like stuff. To me, that's also that. Yeah, there's definitely progress.
I certainly think it's underappreciated by the vast majority of people who aren't in the community, how incredibly hard these materials problems are. I mean, everyone's been spoiled by silicon. And they're like, well, look at how well people can handle devices with silicon and the reproducibility and all this stuff. And the answer is, of course, that's the result of thousands and thousands of person hours or person years of effort. And the result of, it's the end result of, you know, sort of a 7-decade research program in some sense. So, you know, the fact that this hasn't all been wrapped up in a bow in less than a decade should not really surprise anybody.
Although it's also true that some materials could be better than others, right? We could be incredibly lucky with silicon that allows us to, you know, post tweets and stuff. You know, other materials may just be harder.